Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Identify the starting material and first reaction. The starting material is gamma-butyrolactone, GBL, a 5-membered cyclic ester. Treatment with IChCl opens the lactone ring to give 4-chlorobutanoic acid, Cl, CH2, 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 Then, 2-SOCl2 converts the carboxylic acid to the acid chloride, giving 4-chlorobutanol chloride, Cl, CH2, 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 COCl. This is compound A. Moving on to the next step. Friedel-Crafts acylation of benzene. Compound A is equal to 4-chlorobutanol chloride reacts with benzene, PHH, in the presence of UlCl3, Friedel-Crafts acylation. The acyl chloride end reacts with benzene to give PHC is equal to O, CH2, 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 Cl. However, under these intramolecular Lewis acid conditions, the pendant chloride can undergo intramolecular Friedel-Crafts alkylation or the 4-chloro group cyclases. More precisely, after the Friedel-Crafts acylation gives PHC is equal to O-CH2, 3Cl, the UlCl3 can promote intramolecular cyclization. The terminal chloride undergoes intramolecular Friedel-Crafts alkylation onto the phenyl ring to form a cyclic ketone, specifically alpha-tetralone, 3,4-dihydronaphthalane 1,2H1. This is compound B is equal to alpha-tetralone, a bicyclic compound, benzene ring fused with a cyclohexanone ring. Wait, let me reconsider. With 4-chlorobutanol chloride and UlCl3 benzene, Friedel-Crafts acylation gives PHCO CH to CH to CH to Cl, 4-chloro-1-phenylbutane 1-1. Then intramolecular Friedel-Crafts alkylation closes the ring to give alpha-tetralone, a 6-membered ring ketone fused to benzene. So B is equal to alpha-tetralone. And for the final step, KOH-MeOH treatment of alpha-tetralone. KOH in MeOH is a base-induced elimination, E2 or E1CB or retroaldol. For alpha-tetralone with KOH-MeOH, this is an aldol-type base treatment. Actually, KOH-MeOH on alpha-tetralone, the base deprotonates alpha to the carbonyl, but since it's cyclic, elimination would open or modify the ring. Under harsh base conditions, alpha-tetralone can undergo ring opening via retrodiachman or retroaldol. Actually, reconsidering, KOH-MeOH causes E2 elimination in the ring of alpha-tetralone to give to H-naphthalene 1,4-A1 or beta-naphthal. More likely, the beta-keto system in the ring undergoes base-mediated elimination to give PHC is equal to O, CH is equal to CH, CH3. No. Let me reconsider B. If B is equal to pH, CH to CH to CH to Cl, no cyclization yet, then KOH-MeOH on pH, CH to CH to CH to Cl gives intramolecular aldol or elimination. KOH-MeOH on a haloketone, the base deprotonates alpha to carbonyl, then intramolecular SN to displacement of Cl gives a cyclopropyl ketone. PHC is equal to O, cyclopropyl. This is compound C is equal to option C. So the revised pathway, A is equal to 4-chlorobutanol chloride, B is equal to pH, CH to CH to CH to Cl, Friedel-Crafts acylation product without cyclization, i.e., 4-chloro-1-phenylbutane 1-1, C is equal to PHC is equal to O, cyclopropyl, phenyl cyclopropyl ketone, via intramolecular base-promoted cyclization, deprotonation alpha to C is equal to O followed by intramolecular SN2 on the terminal chloride-forming cyclopropane ring. Why other options fail? A. PHCH2C is equal to O, cyclopropyl, wrong connectivity, CH2 between pH and carbonyl not consistent. B, PHCH is equal to CHC, is equal to O, CH3, chalcone type, not consistent with this pathway. D, PHC is equal to O, CH is equal to CH, CH3, elimination product, not cyclization. Therefore, the correct answer is C. Therefore, the correct answer is option C.